Tres. Okay. Johnny, if you can just stop sharing your screen for the moment. Okay, good afternoon, everyone. Welcome back to the second day of the MECHS conference here in coinciding with the University of Purdue and the Universidad de Valle here in Colombia. So yesterday we had some great talks and we're ready to move on to our second theme. So I wanted to first present our leaders of the subgroups for the discussion. They're going to be James M. Rickles, Jim Rickles, and Oh-Sung Kwon. I hope I'm getting the names right there. So that will be in the second half of our presentations today. Hopefully we can get through the, have a bit more conversation because we won't have the long welcome. So I'm just going to quickly remind you of our speakers. We're going to have first up Johnny Wilfredo Condori Uribe from here in Colombia. And the second one is Barbara G. Simpson. So without further ado, I'd like to again welcome you all back to the second day, and we'll jump straight into Johnny's talk. Johnny, you'll have about 18 to 20 minutes, and then hopefully we'll have some time for questions at the end.
Okay. Hi, everyone. Today I'm going to explain what CyberMech is, what are the benefits of using this parallel platform, and how to exploit its features, and the benefits for real-time hypersimulation. So I'm going to go through the outline briefly. I will present an introduction, then I will present some challenges and motivation. Then I will explain what is CyberMech, and then I will show some cases, some examples for exploring parallel computing in RTHS, and then I will show a couple of examples of what I'm currently doing as my research project. So let's say we have this 5-story building, and imagine that the first story is going to be built of some unknown material. So what we do is we split the complete structure, and we model as a numerical system, the upper part of the building, and we build the bottom part of the building in the laboratory. And then we connect these two subdomains using this transfer system, and we connect it in a closed loop, in the feedback loop, in real time. So, however, we have been using mainly and successfully these simplified models in sequential computational platforms. And there's nothing wrong with that. This allows us to explain the global behavior of the building. But what happens if we need to see what is there to investigate, what is the local effect of the failure in the column? So for that, we need different models. Let's say 4 years ago, this MECHS project started, and then we got together in 2 previous workshops, and we came up with some barriers that need to be overcome to extend the application of hypersimulation. And for me, I have been focusing on the design of control systems for the transfer systems, also real-time parallel computation platforms, and especially nonlinearities and uncertainties. So, but now I'm just also including this complex boundary conditions and benchmark problems definitions. So I'm tackling also multi-failure RTHS problems. But in this conversation, I'm going to talk about especially real-time parallel platforms. So what is CyberMech? CyberMech actually is it's composed of 3 elements, 3 pieces of code, and also it's a collaboration of a team of teams. Let's say first we have this real-time parallel engine. We call it a clustering launcher, which schedule all the tasks and the resources for the computer, and is developed by these computer scientists in Washington University in Southeast. And then we have the finite element solver, which do the analysis of the structure, and then here in Purdue. And then I have developed the hypersimulation management platform, which provides tools for modeling state space systems, nonlinear models, controllers such as the PID, robust linear controllers, nonlinear controllers, Harman filters, particle filters, and handler signals as well. So actually, the HSM is the interface to design the RTHS experiment. And this 3 codes resides in a Linux machine with a real-time patch and is written in C and C++. So how this works in CyberMech? Here you can see this in the top, these 3 rectangles that represents the 3 cores. And let's say the CyberMech has true parallelisms. And this means that for a system to have true parallelisms, it needs to be implemented first inter-task parallelism, which means that different tasks can be sent to different cores. But at the same time, it needs to have intra-task parallelism, which means that different tasks or one task can be split into different cores in this sense. So it's worth mentioning that this system is designed for computers off-the-shelf machines. So why do we need these parallel computing systems? Well, to improve the quality of RTHS, and we do this by increasing the number of the degrees of freedom, also to doing higher frequency tests, and also developing and implementing advanced controllers. In this case, let's want to focus on this specific topic. This is let's say the sketch for the real-time hyper simulation. You have MECHS substructure on the left. You have the physical substructure and the plant actually, and the controller in the middle that compensate for delays and dynamics for the transfer system. And something that is very important is that all these tasks needs to be computed within every time step. And that's when we are make sure that we're conducting actually true real-time experiments. So let's say we have this frame here, and then let's assume that this device here is a non-linear device, a unknown device. Usually we do the RTHS by model the system as simplified degrees of freedom, and then we build or mount this device in the laboratory. But in this case, we are using CyberMech, so we're going to use these finite element models, finite element software, and actually I'm going to just mesh the columns and using models from 10 degrees of freedom up to 1,000 degrees of freedom. So we have the MECHS substructure here, the plant on the other side, and the real controller, which is a robust linear controller in the feedback loop. And actually what I use is the 24 cores machine here. It's worth mentioning also that this code CyberMech resides in only one machine. There is no need to have a target and a host machine. So you develop the experiment here, you compile the system in the same machine, and you run it in the same machine as well. So you have some decision hardware, the servo hydraulic controller here, which communicates to the plant, and we form the closed loop in this way. And when we tried this example with some nonlinearities, we were happy to know that those cases using finite elements of the frame from 10 degrees of freedom up to actually 1,000 degrees of freedom were successfully without instabilities, and the responses were similar between each other, which is pretty good. And then in terms of tracking performance, you can see here in the x-axis the desired displacement and the y-axis the measure displacement. And the idea is that perfect tracking control is when we have a straight line, which doesn't exist in real life in the laboratory. So this tells us that it's a pretty good accomplishment. But let's compare CyberMech with SpeedLoad. On the left side in blue, we have the SpeedLoad results, and on the right side in red, we have the CyberMech results. So let's say if we are using this 200 degrees of freedom finite element model in SpeedLoad, and this time here represents the time for CyberMech to compute the whole finite element model. And if we do the same for CyberMech, and both running in a sequential functions that is using just one core, you can see that there's a speed up of 5 times compared to speed load. Actually, speed load or this Simulink or MATLAB doesn't have these built-in functions to model finite element, but we did it using this RT frame 2D for sake comparison. And then what happens if now we double the number of degrees of freedom model to 400? In this case, this number here, the computational time for speed load at every time step is very way in the lower side for the typical sample frequency that we use in RTHS. But thanks to CyberMech parallelism features, we activate this parallel component, and we're able to run in a very short time, which is about 30 times faster than speed. So then what we do is just to increase the number of degrees of freedom of the finite element model and reach 1000 degrees of freedom. Well, the speed load cannot handle this because it's sequential in this set of experiments. So then another way to improve the quality of RTHS is to using advanced controllers and higher frequency tests. But why do we need advanced controllers, and why do we need to worry about these techniques? So let's say in this case, here we have big MR dampers, and in those experiments, these MR dampers went from passive on to passive off, back and forth, and the controller was a linear controller, and it shows instabilities. So because of this, it's actually it has many causes, but in general, for having a high performance and a high quality RTHS, it's very important to have a control approach able to handle these changes or nonlinearities. So for us, in our case, in our approach, we are dealing with unknown plants and also highly nonlinear plants. And what we develop is a controller that is composed of a nonlinear robust control law and a nonlinear estimator. So let's say if we are trying to control this small shake table, in which the nonlinearities comes from the friction on the bearings and from the control input saturation, we implemented this slide mode control law and the nonlinear particle filter here, particle filter estimator. And the feature of this sliding mode control of this approach is that it needs all the states of the plant model. But on the other hand, this approach doesn't need to have an exact plant model or a model that is very close to the plant. It only needs actually an estimate of the plant that captures only the essentials of the dynamics. And another nice feature is that it allows to implement these uncertainties in the control law and in a very straightforward way. So let's say we have this case one, only the shake table, and we design a controller for this case with all these parameters, uncertainties, and nonlinearities. But then we have another case in which we add around 10 kilograms mass, and then we have another system which is 2.5 kilograms. So what we're going to do is what we have done is to design the controller for case one, and then run the same controller for the case 2 and 3, and see what is the performance when changing these masses, and also in the presence of this highly nonlinearities coming from the friction and the saturation of the input command. So as you can see here, we expected to have this behavior of the performance control, the tracking performance, in the x-axis to have the target displacement, in the y-axis dimensional displacement. And if we increase the mass, obviously we are going to have these wider loops, which means the error is increasing. Actually, the numbers are here, which are pretty good considering that we're dealing with high nonlinearities and uncertainties of this mass. Actually, by the way, I think the mass of this small shake table is around 25 kilograms, which means that this is around 50% additional mass. So, but beyond the tracking control performance, what are the benefits of being able to run higher frequency tests? So as you can see here, in this experiment, we have 3 tasks: the control law, communication overheads, and the particle filter. So the time that it takes for CyberMech to compute each of these tasks it's about these numbers on every time step. And here, the total time step it tells us that we are able to run these experiments at 6,000 hertz. And the impact or the benefits of doing this is the following. So for real-time platforms, the speed code, I have included the speed code here just for reference. We have the 3 cases here. If we use CyberMech and run it at 1,000 hertz, we have similar numbers for speed code. So our experiments, our system works as expected. But as soon as we started increasing the sampling frequency, then the errors also decreases. And for the case 3, which is the worst case, the one that has more changes in the mass, it goes from 7% and these errors down to 2%. So 3.5 times smaller. And that's the advantages for CyberMech is it has true parallelism, and you need only 1 computer off the shelf. It's free. You have a lot of flexibility in developing and implementing algorithms, and you can do higher frequency test execution. And it's very efficient in terms of money as well. So all these amazing people has been also involved in the development of this platform. So what I'm doing currently is that even though CyberMech has a lot of great features, it has also limitations. For instance, it's able to run at a fixed rate, which means that the resources of the computer are fixed during the whole experiment or simulation. And this is where elasticity plays a huge role. And this concept of elasticity is based on handling 2 properties: the workload and periodic rate. So the workload might change in a case. For instance, if in finite element model, the MECHS of the finite element model changes, or if I'm using a particle filter for nonlinear behavior, and I need to switch back to Kalman filter for linear behavior. So the workload can change, and actually the required workload are not unique. So that's a very nice feature to handle. And then we have the sampling frequency of the periodic rate, in which we might need to change the sampling frequency. A very good example is this pounding examples in this pounding issue in base isolation systems. So when there's no pounding, there's some set of constraints, and when we have this pounding, this impact of to the mode wall, then higher dynamics, higher modes are activated, and we need different constraints and different models, and run at a higher frequency to capture this higher dynamic. So if the system has this ability to change the computational workload and the period, we say that it has combined elasticity. And that's what we've done as well. So, but just at the beginning stage, we have tried this as in a virtual control problem, in which we have here a mode changing plant that requires, in this case, the use of the common particle filter. And so this means that this example considers the change in the workload. But because this is a visual control problem, we are also implemented these synthetic tasks that are run along the simulation, but are trying to manage in arrays operations. So we were looking for example that can handle these constraints, the rate and the workload effectively. And the criteria is as follows. Let's say if we define a threshold here, plus minus 0.01, and the system goes nonlinear, And within these limits, the system goes linear. So if the response is in this point, we use the particle filter, and if the response just goes back to this middle zone, we switch to the common filter. And we do this during the whole simulation. This is pretty simple, but proves the idea and more importantly that the platform works using this elasticity behavior. And as you can see here,
I just want to check just so that we have time for questions. If we finish up in about 2 to 5 minutes, we probably will have time.
Sure, thank you.
No worries.
Here is very small, which tell us it's a good progress. And something relevant to say is that you can see here on the left these results. This in the x-axis the workload, and the y-axis the period. On the left axis, on the left side the common filter, and the right side the particle filter. So the blue diamond here responds to the RTHS, and the other one is synthetic tasks. So let's see. The blue one, when it's running with the common filter, it has a workload of almost 500 microseconds, but when it changes to the particle filter, the workload changes. And the same in the same fashion, the workload for this synthetic task 3 is about 2,000 microseconds, and it changes then at 5,000 microseconds. And in the same fashion, in this case, it's different. In this case, we are changing the period here in the synthetic task 1 from almost 2,000 microseconds. It's going down to 1,000 microseconds. And finally, in this case here, the synthetic task 2, which during the use of common filter, it has these numbers for the period and the workload. It changes in particle filter both. So, and all this is happening in real time, concurrently in parallel, and communicating between each other. And besides that, we have more challenges as well. And one thing that we are pursuing is the multi-actor RTHS. So using complex boundary conditions. And this is pushing us to investigate and to extend our platform, our framework to multi-input, multi-output controllers. So in this case, the immediate goal is to come up with a benchmark, the linear RTHS benchmark for multi-actor RTHS. We have here the numerical substructure, and the blue is the physical substructure. And here we have a picture of me and my partner, Manuel Cimarron, in the laboratory. So we have started here, and the goal is to get to the nonlinear behavior, but the immediate goal in the summer is to release this RTHS benchmark for the community. Of course, this is a huge project, huge task, and other people are involved. I'm just working on the controller and the computational resources, but other people are also working on this project in the models, in the finite element models, and in the design of the plant models, nominal models, and developing also the platforms, doing pretty interesting things. And I'm pretty sure that in the next months we're going to release more important results about this project. Thank you.
Okay, thank you so much for that. Okay, like yesterday, what we're going to do for questions is, if you look at the bottom of your screen, there's a little smiley face that says reactions. Click on that and then click on raise hand. Yesterday there was some different hand gestures, but I can monitor all of them now. So if you can raise your hand, we will get to your question. Just bring up my list now. Okay, we have first hand. Might let Gaston go first.
Yes, thank you so much. And yeah, congratulations, Johnny. Very interesting work that you have done so far. I have a quick question. So CyberMech has a finite element module that you mentioned. I think it's called Bunting FEA. Am I correct?
That's right.
So is that a finite element method or software available for researchers to develop their numerical substructures? How easy is to create models for RTHS test applications?
So these codes, the engine, the clustering launcher, and the bounding finite element code are already available in these groups for Professor Prakash and Professor Gill in Washington University in St. Louis. And the interface for developing or for designing these experiments in real time is in C or C++. So there's no this nice interface of MATLAB or Simulink. We have to implement a line by line, code by code. But that's where I my platform, the Harvard Simulation Management Code, it's useful. So it hides all these low level details, and it has the commands, functions, and objects all ready to be used to model these typical components, dynamic components that we use in RTHS. So we have testing this platform. We have documented the platform, the HSM, and we have provided this user guide. I have built a user guide for this, and we have provided this to new students so that we are sure that this is readable, easy to follow, and ready to be shared with the community. But the goal is that the whole platform should be free.
Okay, thank you. Can I make another follow-up question? I don't know if we have time. So how does your framework compares to using OpenSys and OpenFresco or other coordinators that are available in the field?
Let me. It's here. Okay, so for instance, when that's a good question, and I haven't used OpenSys or other platforms but myself, but my understanding is that, for instance, CyberMech, the finite element codes, the controllers, every piece of task that is designed and implemented in CyberMech runs and is controlled at every time step, and we have the capabilities of monitoring the deadlines missed if there's one, so that we are making sure that that the model is solved within this time step exactly at every time step. We also know if there's some missed deadlines, and we know at what specific time this happens. What my understanding from other platforms, including OpenSys, is that they run the model and they expect the best of the system to be run. They expect the model to run and within the whole time of the simulation. So if that platform can run it, so it might have a good performance. But actually, I don't know how we can make sure that at every time step the solution is provided before the next time stumble just gets to the point. So I think that's my best answer I can provide.
Okay, if we can move on to the question from Professor Rickles.
Yeah, thank you. Sorry, and yeah, Johnny, very, very interesting presentation. I have 3 questions. I'll just try to make them real short, but first one is you noted there's I guess multi-processes and task assigned. And as you know, the problem with multi-cores is the assignment and the allocation of the workload to each. I mean, is that done in a deterministic manner that you can assure that the information comes back in due time, or is it non-deterministic in terms of the allocation of the workload on the various processes? You know, these tasks that have to be performed.
So the actual algorithm, which is the federated scheduling algorithm that uses this this approach, I'm not sure if it's deterministic or not deterministic, but I have to say that this platform is soft real time, so we cannot make sure actually that a model can be run within time set. But what we can do is to test virtual RTHS before the actual RTHS and see if there are missed deadlines for some scenario.
Okay.
But after the simulation, we have like a set of files that show us where each missed deadline happens. But we haven't done those issues so far.
Okay. Okay. Just add two other short questions there. You mentioned degrees of freedom, and so that really dictates the size of the matrices and the multiplication. But another aspect is the types of elements, the number of elements, and the complexity. Can you give us an example or idea of what kind of elements were used in these analysis? If you're able to achieve that amount of time to do those calculations.
So in this case, what we have used is, in terms of finite elements, linear frame elements for the columns. So, well, this is an old machine of like 10 years machine, but we have a new machine that we're going to test now with our experiments. But in terms of finite elements, we have tried these frame elements. We haven't tried shell or other type of elements. So
but basically you've done linear problems to date, right? So there's no state determination, very simplistic. Just k times u is equal to r sub I, right? There's no complex state determination. Okay, that's fine. Yeah, thanks, John. And the very last question is that Kalman filter. It caught my eye there. Do you have any stability problems? Are you using a constrained Kalman filter? You know, because the covariance matrix could become non-positive definite, and you can't take the square root of a negative eigenvalue. So the Kalman filter sometimes breaks down. You have to set limits and constrain it. Did you encounter any issues, or do you have to tune that Kalman filter to make sure that during a test it doesn't go unstable?
Yeah, we have to tune the Kalman filter.
So you basically have to probably set the limits and part of the covariance. You know, there's a covariance there you have to set. So you basically tune it so the eigenvalues stay positive, I guess, right?
Yeah,
Okay.
that's right. We have to do that and make sure that we anticipate all those cases in simulations.
Okay.
We deal with different content of frequency noise, high frequency noise, to avoid these instabilities in experiments.
Okay. Yeah. Thanks, John. That was very informative. Yeah, thank you.
Thank you.
Okay, we're going to have time for just one more question that I've already got here. This person has sent it to me because they have some background noise, so I'm going to read it out. This is from Marco Fernando Alja, and he thanks you for your presentation and has two questions. So the first is, which SpeedGoat target machine model was used for the comparison? Was it baseline, performance, etc.? And the second one is, when you mention off-the-shelf computers for the implementation of CyberMech, how comparable is it to the price of the SpeedGoat machine you used for the comparison, including the DAQ system?
Okay, the price for a computer of these features, the last time we bought one, it was about $5,000. I'm not familiar with how much the SpeedGoat machine would cost, but I think it's very affordable and it's quite effective in that matter. So for the other question, if we are using, the question was, can you repeat the first question? I didn't understand well. It was regarding the model in SpeedGoat as well.
Let me just read it again. So
yeah.
Which SpeedGoat target machine model was used for comparison? For example, baseline, performance, etc.
SpeedGoat target machine. Which model? I don't have the model in mind right now, but we bought that SpeedGoat machine like maybe 8 years ago, more than that, at least.
Okay.
Maybe.
I'm hoping.
I think we have updated the machine.
Okay, hope that answered your question there, Marco. Maybe you can, he said thank you. Okay, great. Okay, we're just got, if you can stop sharing your screen.